Okay. So where did we leave off last week? What did we say we're gonna do next?
So I think last week we were looking at the first method of differentiation by the powers.
All right, so we did unit vector, right?
Yes, sir.
So the next thing now would be differential elements. All right. So, okay. First, we want to deal with the Cartesian coordinates. So we said we were going to basically deal with just three coordinate systems. The Cartesian coordinate, or the rectangular. Cartesian and rectangular is the same thing. The cylindrical coordinate system and the spherical coordinate system. And we were only going to do three coordinates. So in the Cartesian system, we are going to operate in the X, Y, and Z. All right? So when we differentiate with a simple graph, XY graph, and we differentiate dx, dy, that with respect to one coordinate. But in the three coordinate system, we will have to, because now we are representing a point in the X, Y, and Z. Let's go back up here and look at it. The X, Y, and Z. All right? So when we speak about a small change from any specific point, we are talking about a small change in both the X, the Y, and the Z. So if you have a point represented by a value in X, a value in Y, and a value in Z, a small change of that point would be X plus the differential change in X, Y plus the differential change in Y, and Z plus the differential change in Z. So dx, dy, dz are differential change in X, Y, and Z. Clear so far?
Can you repeat that one, sir?
We have a point in a room. The coordinates for that point, you go, I think we stop here. The coordinate for this point, for a point, you go you go a certain amount of unit in the X, right? You go a certain amount of unit in the Y, and you go a certain amount of unit in the Z. And it brings you to that point, right? Just like how we did the differentiation. If you change your location to here, say some point here, you will have to go X plus a small change in X, Y plus a small change in Y, Z plus a small change in Z to reach here. This is your point, right? So the small change in the coordinates that you move is the dx, dy, and the dz. So I am saying to you, dx, dy, and dz are differential change in length. In the x direction, dy in the y direction, and dz in the z direction.
Following, sir.
With me? So your differential change in length is dx, ax, plus dy, ay, plus dz, az. Okay. So then, you're moving from a point P to some other point P prime. So the distance from P to P prime right, is the absolute value or the modulus of your vector. Remember, you're going from P to P prime. So you change by dx, you change by dy, you change by dz. So the straight line between P and P prime is the modulus of that vector. Let me make it easier. Go back to this one. The length from the origin to your point Q here would be the modulus of x squared plus the modulus of y squared plus the modulus of z squared, the square root of that. So I'm saying now, similarly, the distance from here to some arbitrary point out here would be the modulus of your change in x squared plus the modulus of your change in y squared plus the modulus of your change in z squared, the square root of that. Therefore, dl, which you're distant from P to P prime, would be this. That's your absolute distance. Now, if you think of a volume that your changes create, all right? Just like the volume of a cube is x times y times z. A small volume of that volume would be dx, dy, dz. You have a cube. You have a cube. Right? The volume of this cube would be your x times your y times your z. If you make a small cube with that volume, small cube here, and you call all of these your differential y, your differential x, and your differential z, your differential volume will be dv, which is dx times dy times dz. Following so far? Silent. Yes, silent means consent. Now let's look at surfaces. This surface right here, the one facing you here, is defined by y and z. But the direction of the surface is coming to you. So it's in the AX. So you would define, or in the AX direction. So you would define that surface as 2y plus 3z in the AX direction. So here, ds, your surface vector is ds in the A normal. Here, please, I'm going to ask you just for 2 minutes. Someone just drove in that I was expecting to give a receipt to. So just give me two minutes, please. Thanks. Yeah, I'm coming. Yes, class. Sorry for that, and thanks. Okay. So we were at DS. So DS is your differential surface. And the direction of this, the normal would be the AX. So, okay. If we look back at the cube, we have the side coming to us that we just look at. That would be the YZ plane in the AX direction. To the back, I shouldn't erase the little cartoon. To the back, so here then, you have the YZ plane in the AX direction. So for the cube, you would have the YZ plane in the AX, and on the back, you would have the YZ plane in the minus AX. On this side, you would have the XZ plane, and the normal would be in the Y direction. So it'd be the XZ plane in the AY, and this way, you would have the XZ plane in the minus AY. For the top, you would have the XY plane in the AZ, and on the bottom, you would have the XY plane in the minus AZ direction. So you would have 6 differential surfaces, or 6 surfaces to define the cube in the Cartesian coordinates. Okay. Any question for the Cartesian coordinate?
Not right now, sir.
No, sir.
Sir, AX, right, sir, that would be the distance from the differential vector surface area.
Come again?
For the AX, sir, right?
Mhm.
The value for that will be the distance from the differential vector surface.
You mean if we look at the, say the differential vector surface coming to us, which is dy dz. Ask the question one different way.
But I'm going to ask it if me see values with it, like an example or something.
No, man, I can't still ask. But let's capture it right here. Ask the question.
Right. The value for AX, where would I find that, sir? Will that be a distance value?
No. All right. Remember, like we said, in the scalar system, right? We have a unit vector, which is 1. We have a unit for the scalar, which is 1, right? So if we go into, we would say 1 pound of flour, 10 pound of flour, which is 10 units of 1. The AX, or the small AX, AY, AZ, is the unit vector in that direction. So the unit vector all right. Let me say it right. All right. What is the modulus of 10? Would be, let's see that right.
Sir, 10.
What's the modulus of 10? 10? On that one. All right. think of the unit vector like how you think of 1. Right? So in a specific direction, right? The unit vector. Okay. So the unit is 1. So 20 is 20 times 1. 30 is 30 times 1. And so on and so forth. All right? 1 unit of weight. So we are defining this surface in a specific direction. All right? So it would be the surface times the unit in that direction. The unit is AX. Remember now, from up here, we decide how we're gonna define the unit vector. Or did we? Yeah, man, we did that. No. Okay. But just think of it. Think of it as the unit vector. If you multiply any quantity or any vector times its unit, you should get back the vector, right? Just like if you multiply any scalar quantity by 1, you should get back that quantity. So in a similar way, if you multiply any vector by its unit vector, you should get back the vector. When we say 10, we don't usually put that it's 10 times 1. It's just given. But in vectors, we take into consideration the direction. So the 1 would not be arbitrary, it would be a vector. So we have to specify the unit. I know, before I leave Cartesian, I don't know if I'm fully confused or I'm half confused, but I'd like to get that out of the way. So ask a stupid question. I will laugh after you until after class when I turn off the audio.
Sir, which one did you say is in negative? And which is, yeah, which one is in negative again? For instance.
I said that, let's look at this, right? let's look at this. Look at this cube now. Okay. So this is their origin, right? So this surface here would be some amount of y multiplied by some amount of z. But the direction that's normal to it would be in the ax. So this surface this one surface here would be xy in the ax direction. All right, because, okay, suppose I tell you it's surface xy. It could be either this one or the one behind it, not true? Not the same thing?
Listen.
But is in the ax direction. So you specify that surface now. But how this surface differ from this one over back as now? It would be the same xy, but it would be in the minus ax direction.
That the one on the right, sir.
Hmm?
That is the one on the right.
No, man. This one here. This one here, right? Is the same as this one behind it right there. Just take up a little box and look at it. One side facing you and one the behind.
Yes, sir.
So the one facing you would be, oh shit, this is wrong. It would be y, z, not x. Y, z, sorry. Would be our zy. So this surface would be this times this, right? Length times width would be zy or yz in the ax direction. This surface behind here would be the same yz, but it would be going this way. So it would be in the negative ax direction. So by specifying ax or minus ax, you would know whether it's this surface or this one.
Sir, because they're measuring it about the point P, so it would tell you whether you're going the positive or the negative as they say. So. That is what I take from.
No, but not think of P with what we're doing now. We just use that little thing. Just think of the cube. Think of the cube. The coordinates of the cube is x going this way, y going this way, and z going this way. So we said the cube have 6 sides. take this side out here. This side would be x times z. The direction of this side would be in the AY. So this side here would be x times z. That is x times z, then time width. And the direction, which is the direction normal to it, would be AY. So by saying it now like that, the purpose of the unit vector is that you can differentiate between this side and this one over the back here. This one and this one have the same dimension. But this one is in the AY and this one is in the minus AY. So if I define a plane to you, say a charge is 4x plus 5y coulombs per meter square in the AY. You know it's on this side. If I define it and say it's in the minus AY, it's on this side. Similarly, if I said this side, right, which is y times x, is in the AZ, and the bottom would be in the minus AZ. All right, I'm gonna restart this Zoom thing. Dinner time, so if you don't get it by dinner time Sunday, call me, interrupt me. Because we can't go now, it's Sunday. Sandra Horn is sister in your yard. Okay. I want to do the next system quickly. The cylindrical coordinate system. So here you're gonna think of a jump. Right? This is your origin. Right? So, like in the Cartesian or rectangular coordinate, we have x, y, and z. Say you want to get to a point. Oh, shucks. Eraser. Say you want to get to a point here. Over here. Right? You have to move from your origin, you're coming out, right? And now you have to go around. Right? So what I'm doing, a good plan is and then you have to go up. Right? To come out is R. To go around is phi. And to go up is Z. So while in the Cartesian system is X, Y, and Z, in the cylindrical system it's R, phi, and Z. Those are your coordinates. You with me?
Yeah, man, sir. We're there, man.
So R, you can go from 0, which is at the origin, to as far as you want to go. Infinity. To go around the circle is 2 pi radians. So phi go from 0 to 2 pi. Z, you can go from minus infinity to infinity. All right. So you're going to define a point here at P. Right? So hear me now. A point P, I don't even have to tell you, that is the cylindrical coordinate system. I said, suppose I said a charge of 10 microcoulomb is located at R equal 10 centimeter. Theta, phi by 4, and Z 15 centimeter. It's a done giveaway. It's a cylindrical coordinate system. So you have to come 10 from the origin, go around by pi by 4, and go by whatever I said Z was to find that point. So R so here you are. So R is a constant plane. Phi is a constant, and Z is a constant. So digest this. So in other words, just like how we speak of the sides of the cube in their specific direction. Say a plane R would be a radius R in the cylindrical coordinate system. So that would be your AR. That would be your A normal for the curvature of your cylinder. This is your cylinder. This is half of your cylinder, right? So the direction of this surface defined by this radius would be in the AR direction. That's the direction that's normal to the surface. A plane which is at angle phi, and you notice the angle is measured from the X. So the plane, which would be a slice, like if you slice take a slice out of a tasty cheese, the face of that slice, phi would be normal to that. And if you take the top here, Z would be normal to that. So while you have surfaces in the Cartesian coordinate system, in the AX, AY, and AZ direction, that means these surfaces are normal to the AX, AY, or AZ. In the cylindrical system, they are normal to AR, APHA, and AZ. Those are your unit vectors. Any bright question? Any stupid question? That's all we're bright. So here you are. So all we did was superimpose what's above in one diagram. Okay. So we said this already, but let me say it again using the notes. Similar to the Cartesian coordinate system, there are 3 unit vectors in the R, phi, and Z direction denoted by AR, A phi, and AZ. So here you are. The AR coming this way from the origin. The A phi going that way. Where they put the A phi? Here, A phi going that way. And the AZ going that way. AR for this point, you define this point as 7R AR 6 phi A phi 10 ZAZ. P PR AR P phi A phi PZ AZ. That's your point P here. So if somebody's saying you somewhere in a cylindrical coordinate system, you can just get up and head straight there. Not a problem. The differential elements, just like we have the dx, the dy, the dz, similarly, differential length, dr in the r direction, so this is tricky now. So you're going from the origin, or you're going to define a differential volume here, right? Or you're gonna take a chunk, a small chunk out of your cylinder. This is your differential volume, right? Now, so it's gonna be defined by your R. Your R gets you to this point. Your R plus your dr get you to here. R plus your dr. All right? You need this side and this side, right? If you have a circle, what's the circumference of this circle?
Two pi r, sir.
Okay, 2 pi r. Okay. So 2 pi r. So what's the length of this arc?
Sir, I'm going to have to use to find that, sir.
How they get the 2 pi to be in finding the circumference of the circle, how they get the 2 pi?
Because 2 pi are 360, sir. 360
Right.
degrees.
Yes, the 2 pi is 360, which is the 2 pi is the degree in radians, right? So 2 pi radians is equal to 360. All right? So to find the arc would be that angle in radians times r, right?
Yes, sir.
So here we have it. That differential length is r d phi, with d phi is the angle. So you have 2 sides now. You only to find this other side, which is dz. So you have dr r d phi dz. So your differential lengths would be dr in the ar, r d phi in the a phi, and dz in the az. With me?
Yes, sir.
All right, let me ask you guys. Anybody have class though? Because we're supposed to stop now, but I would just prefer finish this and then before we stop. Let me see if anybody. Everybody want me to continue?
I guess you can, sir. Continue.
Yes, sir, you can continue. No problem with that.
Yes, sir.
Okay. So your differential length, the magnitude from one point to the other would be the square root of your differential length squared, just like in the Cartesian coordinates. And your differential volume would be your multiplied by your differential lengths multiplied together. Just like x, y, and z, dx, dy, dz would be r, dr, d phi, dz. All right. This is what I'm gonna let's stop for the hour because it's raining and that's disturbing me as well. So hopefully the rain will ease in an hour. We'll join back at 1 o'clock. Okay? Let's
All right, sir.
let's get back at 1 o'clock.
Yeah, move up the class now, sir.
Huh?
Yeah, move up the class time now.
I gotta do what?
If you're moving up the class time now.
No 1 o'clock it start back.
No, sir, 2.
2 minutes have, sir.
At 2?
Yeah.
But if you move it to 1, me no mind it, sir.
Eh?
If you move it to 1, me no
I
mind.
think he'd have to inform everybody else.
Hold on, let me check what we have.
At 2 o'clock, the class normally start, man, sir.
I'm 2 o'clock?
Yeah.
Yes, sir.
All right. All right, we start back at 2 then. Okay. 2 o'clock, y'all.
All right, sir.
All right, sir.
All right.